So in the last lecture, I want to talk about adaptive parameter control that I just introduced in my previous lecture. So, solving a multi-objective optimization should be considered by some quality criteria as well, such as coverage error. And later, I will talk about two more quality criteria as well. For example, the coverage error, it tries to, it is the smallest epsilon for which this one is called coverage error. We want to reduce the coverage error. And I will see you why we want to find why it is itself an optimization problem, because we have, for example, three different quality measures, and there is a trade-off between these quality measures as well. For example, for a given coverage error, you have to also minimize the other two quality criteria as well. And the efficient set is not necessarily connected. I will show you with an example. For example, you have something like this. It goes like this. This is the efficient point. This is the efficient point. This is the efficient point. And these are efficient. These are efficient. But there is a gap between these points and these points and these points. So it's not always trivial to say that, okay, your Pareto efficient set is like this, then all of them are connected and there is no gap between them. Sometimes you have a jump from one set to another set. So second measure is uniformity. You want the distance between those minimal points to be equal. And the third one is cardinality. Of course, you have you can count the number of points that you want to propose to your client or investor. And so geometrically, you can say that delta, which is a quality measure, delta so delta is another quality measure, and but it is related to, for example, y1 and y2 are inside your approximation set. But when you're talking about epsilon, it is comparing with the points that you have not considered in your approximate efficient set, and so you want a low delta and a low epsilon simultaneously. So even this one is an optimization problem, because you want to minimize both epsilon and delta. And so you see that this is just another optimization. And so for 2D problem, you can define something like this, and you approximate remember, this is the value function. You approximate it by first order Taylor approximation. And if you just use this, you can also use the first order Taylor approximation for f as well. For example, f is equal to f of 0, because it is evaluated at a0, plus partial derivative of f with respect to a and I minus a0, plus partial differentiation of f with respect to r and r minus r bar, r0, which is r, here is r, And so the partial differentiation with respect to r, as you see, is this coefficient t bar. So t bar goes here, and t bar has the definition here. This is the definition of t bar, and so that's why this holds. And if you use this equation here, if you rewrite it here, we want to distance between those 2 points and the objective space, as I said in my previous lecture. We want to know that the distance between them is alpha. This distance between them is alpha. And so in order to satisfy this, in order to know which points on the hyperplane you should use, because you need to use some A points on the hyperplane H, such that the difference between these 2 points is just keep them constant. And so let's move on and see. So we substitute for f. We approximate it with this function, with this formula, and of course S1 are the bases. S1 and S2 are the bases. If we have a hyperplane H, then if A is inside the hyperplane, you can span this hyperplane by 2 vectors, by vector S1 and S2. Sorry, by vector V, which has the first coordinate of V, and we have a vector. We have 2 vectors, V1 and V2. So span of V1 and V2 is your hyperplane, and S is the amount that you go in that direction on the hyperplane. So we want to design such an amount S, such that if you go in that direction, for example, if this is the first point, reference point that you have discovered, if you go in direction V with amount S, this is the amount you go in this direction, you get another point, another reference point, A1. So we want to find that S. That S is the question, such that the norm, the difference between them, between the points on the efficient frontier, this point and this point, the distance becomes alpha. And if we solve this, we can say that S1 is just alpha divided by this one, because this is just a scalar. So it's very explicit formula. And so we have done for first order approximation, although you can do it for a second order approximation using Hessian, and it is more accurate. And but you need to solve, some equation, some nonlinear equations based on Newton-Raphson method, for example, and it takes time. But you need to deal with these polynomials, and it's a nonlinear problem. For example, for a 2D problem, let's talk about all of these steps. First, I recall you that the gradient of the value function that I talked about is minus mu0, which is the Lagrange multiplier, and we have calculated for our first reference point, which is 2 and 1. So minus 2, 1 is equal to minus 2, minus 1. That's why we have written it here. And we just substituted in this formula, and also we designed S1, the amount that we go in that direction. So if we just calculate S1 is alpha, what is alpha? Alpha is 20 here. For an equidistance of alpha, for example, on the efficient frontier, the distance between 2 minimal points is alpha. So 20 divided by this norm is equal to, for example, then we calculate it, and S becomes 4 and 5. And so you can use you can understand which A you need to know because A is equal to A0 plus ASV. And for all the points inside the hyperplane, you can do such things as well.